form at the same time and so are observable physical evidence that this abundant nuclear decay had to have occurred at an accelerated rate. Now, this is all written up in detail in the second volume of the rate research, and there's other diagrams and there's a step-by-step explanation of the way in which the experimental data, there is experimental evidence that hot fluids, hot waters, go through the biotite flakes and are capable of transporting that polonium, where it nucleates in certain sites between the pages of the book nearby to produce those polonium radiohalos. So let me just run through it quickly again, because I want to take this a step further. In further research, I've actually been testing this idea of the formation of polonium radiohalos. I say, okay, this is a model for their formation. Now let me make predictions, which is what a good scientist does. He builds an idea, and based on that idea, he predicts what effects it will have in other situations, in other rocks, and then he goes out and collects samples to see if his predictions are correct. And this is exactly what I've been doing in research subsequent to the conclusion of the RATE project. So let's just run through this idea again of how the halos form side by side. We've seen that diagram before. The radiohalo, now an interesting extra thing in this is discovered that the radiohalos can only form below 150 degrees Celsius. Otherwise, the alpha tracks, the little particle damage trails, are annealed. That is, they're wiped out. Let me explain that to you. When the alpha particle goes through the crystal lattice like the wall, it damages the crystal. That is, it pushes the atoms of the crystal structure out of alignment. Okay? You heat the rock up, you heat the crystal up, what does it do? The heat transfers to vibrational energy of the atomic structure. So if you get enough heat, the atoms will vibrate sufficiently so that the atoms that are being pushed out of place will pop back into place, back to the original structure of the mineral, which will heal the damage caused by the alpha particles. So in other words, the dark discoloration disappears. Now, how do we know that's 150 degrees? Well, interestingly, in the same drill hole in New Mexico, where Russ Humphreys got those zircon crystals for his helium diffusion studies, as you go down that rock, that granite, they actually measured the in situ temperatures, the current temperatures in the rock as you go down. And they also looked in that granite at the radiohalos in that granite. And when they got to the depth at which the rock temperature was 150 degrees, the halos were faded. Below that, at a higher temperature, the halos had been eradicated from the rock. So in other words, temperature will wipe out these halos. The inverse to that is that the halos will not form above that temperature, because the atoms will be vibrating so much that the alpha particles will push them apart temporarily and they'll snap back into position again because of the energy from the heat. So that was an important clue, that they can only form below 150 degrees. Now, we've already said that the uranium radiohalo forms around the tiny zircon crystals. The uranium decay in the zircon crystals supplies both radon and polonium. Radon is the precursor in the decay chain to polonium. Radon is a gas. It's inert gas. It doesn't chemically bond with anything. And it has a very short half-life, but it's very soluble in water. So it also can be dissolved in the hot water coming along, just as the polonium will be in these hot water or hydrothermal fluids. So we have the hot water flowing along between the sheets of the biotite, between the pages of the book. It passes the uranium-rich zircon crystal that's producing radon and polonium, and they're dissolved. Okay. The hydrothermal fluids transport the radon and the polonium to adjacent deposition sites without leaving traces, and the polonium concentrates in new pockets called radiocenters, these new areas that form the centers of these halos. And as each polonium atom concentrates, it decays, but more polonium is coming in the fluids. So as each polonium decays from that site, another polonium atom comes. So rather than all the polonium arriving all at once, which Robert Gentry said it had to do, the hot water flowing through progressively supplies the needed polonium to form the radiocentre, the centre of that polonium radiohalo. So what happens is you have a sulphur atom or a chlorine atom sitting here between the pages of the book, and polonium just loves sulphur and chlorine, and so as soon as it gets there, it stops. Once it stops there, it decays, and then the sulphur doesn't have any polonium sitting next to it, but the water brings another polonium atom along. It holds on to it, but then the polonium decays, so now the sulphur is free to grab another polonium atom. And so over a short period of time, more and more polonium keeps coming across, decaying and producing that radiohalo. So that's this idea of hydrothermal fluid transport to form these polonium radiohalos.
So does polonium come out of the zircon?
Yes.
Helium would be diffused?
Yes. Yes. Correct. And so does radon gas.
Why doesn't it decay so really quickly in the zircon?
Sorry?
Why wouldn't the polonium, like polonium...
Well, some would. Some does. And that produces the polonium rings around the uranium radiohalos. Okay? Some does decay doesn't get transported, and it forms the rings around the uranium radiohalos. Some doesn't, and it gets transported.
Can you measure the distance between the uranium halo and the polonium-210 halo?
You can measure distances. It's very hard. It's very hard to do it consistently by the methodology that I'm using, because what happens is you have to crush the rock and peel the flakes apart, and you don't always get enough of more than one halo in the fragment of the biotite crystal. It's only if you get some of those photographs were actually taken in whole rock microscope slides. So I haven't had enough samples or enough